Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In 18th century Scotland, a vibrant intellectual environment existed, mirroring the reactions chemists were beginning to study. The Scottish Enlightenment, a period of intellectual flourishing, supported scientific inquiry. Universities in Glasgow and Edinburgh became centers for new ideas, drawing brilliant minds seeking to understand the natural world. Scientific understanding was developing, especially regarding fundamental concepts like heat and the nature of matter. The accepted knowledge of the time, often based on ancient philosophical traditions, struggled to explain observations with the precision and rigor that a new generation of scientists required. This was the era of the phlogiston theory, a framework that provided a language for understanding combustion and other chemical processes. This era presented challenges, a time when the fundamental components of matter and the processes governing them remained mysterious. Joseph Black was born into this environment, a person whose contributions would reshape our understanding of chemistry and physics. Black's early life, characterized by a thirst for knowledge and keen observation, established the basis for his groundbreaking work. Born in Bordeaux, France, in 1728, to a Scottish merchant father and a mother of Scottish descent, Black began his formal education at the University of Glasgow, a center of intellectual activity. There, he encountered a curriculum that, while still based on classical learning, increasingly embraced the scientific spirit of the age. Black's early studies, like those of many aspiring scientists of the time, included a wide range of subjects. He learned from professors such as Francis Hutcheson, a philosopher who emphasized empirical observation and rational inquiry. These intellectual influences, combined with a growing scientific community in Glasgow, were formative. This environment fostered critical thinking and encouraged challenging established beliefs. Hermann Boerhaave, a physician and chemist, significantly shaped Black's intellectual growth through his emphasis on systematic experimentation and the application of quantitative methods to chemical analysis. Black also studied mathematics and natural philosophy, acquiring tools he would later use to analyze the physical world. Effervescence, a seemingly simple phenomenon, initially captured Black's interest and spurred his most important discoveries. Substances like chalk, when combined with acids, produced vigorous bubbling, a visually striking and puzzling release of gas. The prevailing understanding of air at the time was rudimentary, considering it a single, indivisible element supporting life and combustion. The chemical reactions during effervescence resisted easy explanation within this framework. What was the nature of this released air? What role did it play in the chemical processes? What precisely happened when chalk appeared to dissolve in acid? Black's solution, a result of his meticulous experimental approach and deep understanding of chemistry, was the discovery of fixed air, now known as carbon dioxide. He showed that this air, released during chalk effervescence, possessed distinct properties differing from the air we breathe. Fixed air could extinguish a flame, a property distinguishing it from ordinary air, which supports combustion. He also demonstrated that it was heavier than air and could be absorbed by certain substances. Black's careful observations and experimentation revealed that fixed air was a distinct entity, a chemical compound crucial to various processes. Black's work on fixed air extended beyond simple observation. He explored the quantitative aspects of the reactions, moving toward approaches that emphasized measurement. He used the balance, a tool that enabled him to measure the weights of reactants and products with great accuracy. By carefully weighing the chalk and the acid before and after the reaction, he quantified the amount of fixed air released. This quantitative approach, a characteristic of his scientific method, enabled him to establish the conservation of mass in chemical reactions, a principle fundamental to modern chemistry. He documented his experiments meticulously, providing precise measurements and detailed descriptions of his procedures, setting a standard for scientific rigor that influenced generations of chemists. Black's work on fixed air remains profoundly relevant. His discovery laid the groundwork for understanding basic chemical reactions, particularly acid-base reactions. The concept of fixed air is central to understanding the role of carbon dioxide in the environment. The study of carbon dioxide is essential to understanding climate change, the greenhouse effect, and the complex interplay of chemical processes that govern the Earth's atmosphere. The industrial production of substances like sodium carbonate or soda ash, a vital component in the manufacture of glass, relies on processes that utilize Black's discoveries. The breath we exhale, the bubbles in our fizzy drinks, all find their roots in Black's pioneering work. His insights into the nature of fixed air continue to inform and shape our understanding of the chemical world, demonstrating the enduring legacy of his groundbreaking contributions. Having established the foundation for his scientific approach, Joseph Black turned his attention to a phenomenon that would revolutionize the nascent field of chemistry, the study of fixed air, or what we now recognize as carbon dioxide. The scientific landscape of the mid-18th century presented significant challenges. Precise measurement, a cornerstone of scientific inquiry, was still developing. Chemists frequently depended on qualitative observations and descriptive reports, lacking advanced tools and techniques for quantitative analysis. Black, however, possessed an inherent grasp of the significance of rigorous experimentation and the power of precise measurement. He understood that true progress in understanding chemical processes required a shift from observation to meticulous quantification. His investigations into fixed air began with an examination of magnesia alba, a white solid produced by heating magnesium carbonate. This substance, when heated, underwent a transformation. It lost weight and, concurrently, released a gas. This observation initiated Black's groundbreaking work. He meticulously weighed the magnesia alba before and after heating, precisely measuring the weight loss. The released gas, which he called fixed air, proved heavier than atmospheric air. This initial observation was a critical departure from prior understanding. The prevailing belief was that substances, when heated, simply decomposed or changed form, with any air produced considered a byproduct. Black's experiments demonstrated that fixed air was a distinct substance, a constituent of the original material, and that its release resulted in a measurable change in weight. Black's approach to experimentation was remarkably innovative for his time. He quantified the reaction. He weighed the reactants and products, meticulously tracking the conservation of mass. His dedication to quantitative analysis set his work apart, establishing a new benchmark for chemical investigation. He created innovative methods for gathering and analyzing fixed air. He utilized a pneumatic trough, a tool for collecting gases over water, a technique gaining wider use. Black's application of this apparatus was marked by precision. He meticulously controlled experimental conditions, ensuring accurate measurements. He also developed methods for reacting fixed air with other substances, observing the creation of new compounds and the release of fixed air. A key experiment involved the reduction of fixed air with alkaline solutions. He showed that these solutions could absorb fixed air, forming a new substance. He then demonstrated that an acid could release the fixed air from the substance. This carefully documented process revealed the reversible nature of the reaction, providing further proof of fixed air's distinct identity. He observed that passing fixed air through a lime water solution caused cloudiness. This observation, combined with his quantitative measurements, led him to conclude that fixed air combined with lime water to create a solid precipitate, calcium carbonate. The reverse process, the release of fixed air from the precipitate upon acid addition, strengthened his understanding of the chemical transformations. The impact of Black's work extended beyond the laboratory. His discovery of fixed air offered a framework for understanding various chemical reactions. He showed that fixed air was involved in respiration and fermentation. He recognized that the gas was produced during charcoal burning and the decomposition of organic matter. He correctly identified fixed air as a component of carbonates, like chalk and limestone, and that acids could release it. These observations formed interconnected parts of a larger puzzle, leading to a coherent understanding of the chemical world. His experimental methods were designed to eliminate sources of error. He focused on the purity of his reagents, the accuracy of his balances, and the control of experimental conditions. He repeated his experiments multiple times, ensuring the reproducibility of his results. Reliable scientific knowledge required careful observation and rigorous validation. His work reflected a deep commitment to the principles of scientific inquiry. Black's work on fixed air had a profound impact. It demonstrated the conservation of mass in chemical reactions, a fundamental principle of chemistry. It established the importance of quantitative analysis, transforming chemistry into a quantitative science. It introduced the concept of a specific gas having a distinct identity and playing a role in chemical transformations. This work laid the foundation for modern analytical chemistry, emphasizing the importance of accurate measurements and the concept of stoichiometry, the quantitative relationship between reactants and products in chemical reactions. Black's meticulous approach to experimentation, his innovative techniques for measuring chemical reactions, and his unwavering commitment to quantitative analysis set a new standard for scientific inquiry. His work on fixed air was a systematic exploration of the chemical world, guided by a deep understanding of the principles of scientific investigation. His legacy extends far beyond the specific discoveries he made. He provided a model for future generations of scientists, demonstrating the power of rigorous experimentation and the importance of precise measurement in unraveling the mysteries of the natural world. Having established the foundational role of fixed air in the burgeoning field of pneumatic chemistry, Joseph Black then focused on another complex aspect of heat, a domain where understanding was in its early stages. The scientific community of the 18th century had a basic understanding of heat, often viewing it as a fluid, the so-called caloric, that moved between objects, determining their temperature. This model, while providing a basic framework, did not fully explain many observed phenomena, particularly those involving changes of state, such as the melting of ice or the boiling of water. These processes absorbed or released heat without a corresponding change in temperature, a puzzle that required a more detailed explanation. The caloric theory, while offering a basic explanation of heat transfer, struggled to accommodate these observations. It lacked the conceptual tools to distinguish between the heat that altered a substance's temperature and the heat that facilitated a phase transition. The lack of this distinction, the inability to account for the hidden heat involved in these transformations, presented a significant challenge to a comprehensive understanding of thermal behavior. This was the intellectual landscape Black explored, a world where the observable effects of heat presented a challenge to the existing theoretical framework. He sought to understand how heat interacted with matter, especially during those crucial moments when a substance changed its physical form. Black's genius lay in his ability to move beyond the limitations of the existing framework, to formulate a new concept that illuminated the hidden dynamics of heat. He proposed the existence of latent heat, a term that captured the essence of his insight. Latent heat was the heat absorbed or released during a change of state, such as melting or boiling, without causing a corresponding alteration in temperature. This concept offered a significant departure from the prevailing view. It suggested that heat could exist in two distinct forms: sensible heat, which was measurable through temperature changes, to latent heat, which remained hidden, influencing the internal structure of a substance during a phase transition. To demonstrate this revolutionary idea, Black devised a series of elegant experiments, each meticulously designed to reveal the workings of latent heat. An experiment involved the melting of ice. When ice was added to water at 0 degrees Celsius, the ice melted, drawing heat from the water. The temperature of the mixture stayed at 0 degrees Celsius until all the ice became water. After the ice fully changed into water, the temperature began to increase. This observation showed that the heat absorbed by the ice, the heat needed to change from solid to liquid, did not cause a temperature increase. This hidden heat, the heat that enabled the phase change, was what Black called latent heat. Black's experiments also included other phase transitions, like the boiling of water. As water boiled, it absorbed heat, but its temperature remained constant at its boiling point until all the water turned into steam. This supported his idea of latent heat. The heat absorbed during the phase change, the change from liquid to gas, was absorbed without a temperature rise. This confirmed that heat could exist in a hidden form, affecting a substance's internal state during a phase transition. The impact of Black's work on latent heat was significant. His discoveries provided a framework for understanding heat transfer and how matter behaves under different thermal conditions. The concept of latent heat, which separated the heat that changed temperature from the heat that caused phase transitions, improved the caloric theory, offering a more complete and accurate description of thermal phenomena. It was a key moment in the history of thermodynamics, setting the stage for future advancements. The influence of Black's discoveries extends beyond the science of the 18th century. The idea of latent heat is a fundamental part of thermodynamics, a concept that informs our understanding of the physical world. This concept supports the design of refrigeration systems, the understanding of weather patterns, and the development of new materials. From simple processes, like ice melting in a glass of water, to complex industrial processes, the concept of latent heat offers an essential framework for understanding the dynamics of energy and matter. The work of Joseph Black, the person who revealed the hidden heat, continues to shape our understanding of the universe. His work provided a crucial link between the basic understanding of heat in his time and the advanced thermodynamic principles that govern our modern world. It demonstrated the power of observation, careful experimentation, and the intellectual bravery to question established ideas. The 18th century, a time of change and discovery, presented scientists with many puzzling phenomena. Among these, the nature of heat itself remained a mystery, while the effects of heat were easily observed, such as the expansion of materials, the melting of ice, and the boiling of water. A precise, quantitative understanding of heat's behavior was difficult to achieve. Existing theories, often based on qualitative observations, struggled to provide a clear framework for explaining the different thermal properties of various substances. This was the scientific environment Joseph Black worked in, a world where the fundamental principles of heat transfer, thermal capacity, and the very nature of heat were subjects of ongoing discussion and research. A major challenge for scientists was the lack of a reliable method for measuring the ability of different substances to absorb heat. Before Black's work, the focus was mainly on the amount of heat needed to produce a specific effect, such as raising the temperature of water. However, the observation that different materials heated up or cooled down at different rates when exposed to the same heat source suggested a more complex reality. When a piece of iron and an equal mass of water are placed in contact with a flame, the iron warms more quickly. The challenge was to measure and to compare these differences systematically. Black's brilliance allowed him to convert these observations into measurable data. He designed clever experiments to measure the heat-absorbing abilities of different substances. His approach involved careful observation, experimentation, and an exceptional ability to gain insights from simple occurrences. Having already revolutionized the understanding of latent heat, Black shifted his focus to the amount of heat needed to raise the temperature of equal masses of different substances by the same amount. He measured the temperature changes of substances when exposed to a known amount of heat. For example, he placed measured quantities of water, metals, and other substances in contact with a heat source. By carefully monitoring the temperature of each substance over time, he determined the heat needed to raise the temperature of a given mass by a specific degree. The experiments were conducted meticulously, with careful control of variables and minimal heat loss. Analysis of the results revealed a previously unknown property of matter-specific heat capacity. Black's experiments showed that different substances have varying capacities to absorb heat for a given temperature change. He observed that water required a significantly greater amount of heat to raise its temperature by 1 degree compared to an equal mass of iron. This difference, he understood, was intrinsic to the substance. The specific heat capacity, a term that would be introduced later, quantified this inherent property. It represented the quantity of heat required to elevate the temperature of a unit mass of a substance by 1 degree Celsius. The introduction of specific heat capacity fundamentally altered the comprehension of heat, incorporated the material's properties beyond mere temperature fluctuations. This concept enabled scientists to forecast and interpret the thermal behavior of diverse substances under different circumstances. It provided a structure for understanding why certain materials heated rapidly while others resisted temperature changes. The consequences were extensive. Black's insights clarified a broad spectrum of commonplace occurrences. A metal pan heated faster than the water it held because metal, with its lower specific heat capacity, absorbed heat more easily, resulting in swift temperature increases. A hot bath retained heat longer than a hot metal object because water, possessing a higher specific heat capacity, could store more heat at a given temperature. The understanding of specific heat also proved essential in explaining the behavior of substances during heating and cooling. Adding heat to a substance would either elevate its temperature or, as Black had shown, alter its state. The specific heat capacity determined the degree to which the temperature would rise for a given amount of heat absorbed. When a substance cooled, it would release heat. The rate of cooling depended on its specific heat capacity and the surrounding environment. Black's work on specific heat facilitated prediction and control. Engineers found the knowledge of specific heat critical for designing efficient heat engines, refrigeration systems, and other thermal devices. Understanding how different materials absorbed and released heat was essential for optimizing performance and minimizing energy waste. For materials scientists, specific heat became a key property in characterizing substances and predicting their behavior in various applications. Today, the concept of specific heat remains a cornerstone of thermodynamics and materials science. It is a fundamental concept taught in introductory physics and chemistry courses, and it is used extensively in a wide range of scientific and engineering disciplines. The specific heat capacity of a substance is a critical parameter in calculations related to heat transfer, thermal expansion, and other thermal properties. It is essential for designing buildings, automobiles, and countless other technologies. Black's exploration of specific heat provided the foundation for a more comprehensive understanding of thermal properties. His work, characterized by meticulous experimentation and insightful analysis, transformed the study of heat into a quantitative science. The legacy of his work, the concept of specific heat, is woven into the fabric of modern science and continues to influence our understanding of the world around us. It is a testament to the power of observation, careful measurement, and the enduring impact of intellectual curiosity. The conceptual framework that Joseph Black established, particularly his work on specific heat, resonated profoundly within the scientific landscape of his era, a period witnessing an evolving understanding of heat itself. The initial understanding was incomplete. Scientific thought at the time grappled with the nature of heat, leading to the development of the caloric theory. This theory described heat as an invisible, weightless fluid termed caloric, which explained many thermal phenomena. This model, a vital step in the development of thermodynamics, was eventually replaced. Black's experimental precision and measurements supported the caloric theory, even though he did not fully endorse it. His work, particularly his detailed studies of latent and specific heat, provided the experimental foundation for the theory. His observations regarding heat absorption or release during phase transitions, like melting or boiling, offered strong evidence for a substance that could be absorbed or released without a temperature change. This observation, the basis of latent heat, matched the caloric theory's core idea that heat was a substance that could bind to matter. The caloric theory offered a way to understand Black's observations. The caloric fluid, according to this theory, could combine with substances, increasing their internal caloric content and raising their temperature. Black's concept of latent heat, the energy needed to change a substance's state without altering its temperature, was naturally explained within this framework. The caloric fluid, in this instance, was absorbed by the substance, changing its state from solid to liquid or liquid to gas, without changing the kinetic energy of the particles. The caloric was essentially hidden within the substance, hence the term latent. Similarly, Black's work on specific heat, the amount of heat needed to raise the temperature of a unit mass of a substance by 1 degree, also aligned with the caloric theory. Black found that different substances needed varying amounts of caloric to achieve the same temperature change. This observation was explained by the caloric theory by suggesting that different substances had different abilities to hold the caloric fluid. The specific heat became a fundamental property of each substance. Black's experiments offered crucial empirical support for the caloric theory. His careful measurements and the concepts he established, latent heat and specific heat, were readily incorporated into the caloric framework. The theory provided a coherent narrative connecting the observed phenomena of heat transfer and temperature change. The caloric was considered the agent of heat, the substance flowing from warmer to cooler objects. Black's work provided the means to quantify this flow and understand its effects. His work's impact extends far beyond its immediate support for the caloric theory. His meticulous experimental approach, his emphasis on precise measurement, and his insightful analysis laid the groundwork for the development of thermodynamics. The quantitative framework he established provided the tools necessary to move beyond qualitative descriptions of heat and to understand heat as a measurable, quantifiable phenomenon. The foundation laid by Black remains critical to understanding the historical development of thermodynamics. Even though the caloric theory later proved incomplete, his precise measurements and the concepts he introduced were instrumental in shaping the direction of scientific inquiry. The experimental data he generated, the relationships he uncovered, and the methods he employed all contributed to the eventual development of the kinetic theory of heat, which superseded the caloric theory. The legacy of Black's work is evident in the modern understanding of heat and thermodynamics. His concepts of latent and specific heat remain fundamental principles taught in introductory physics and chemistry courses. The values he determined, although refined through subsequent research, provided the initial data that scientists used to understand the thermal properties of matter. His work represents a crucial link between the earlier, qualitative understanding of heat, and the modern, quantitative science of thermodynamics. Black's contributions supported an existing theory. His work demonstrated precision and experimental rigor. His meticulous approach, careful measurements, and insightful analysis of experimental results established a standard for scientific inquiry. This commitment to careful observation and quantitative analysis enabled scientific breakthroughs that revolutionized the understanding of heat. Black's work bridges the gap between observation and explanation. His investigations provided quantitative tools that allowed scientists to describe thermal phenomena and construct a comprehensive theory. The concepts he developed and the experimental methods he pioneered continue to resonate within the scientific community. His work stands as a testament to the power of careful observation, rigorous experimentation, and intellectual curiosity. The investigations into heat and its properties, the careful measurements, and the insightful analyses define Joseph Black's scientific endeavors, contributing to a legacy that extended far beyond his laboratory. His influence permeated the academic landscape, shaping generations of scientists through his dedication to teaching and the cultivation of a rigorous, experimental approach to scientific inquiry. Black's impact on the scientific community was amplified by his role as an educator, a mentor, and a champion of the experimental method, leaving an indelible mark on the development of scientific thought. The 18th century witnessed a burgeoning interest in scientific knowledge, yet access to formal scientific education remained limited. Universities, while centers of learning, often prioritized classical studies and philosophical debates. The dissemination of scientific knowledge, particularly the experimental sciences, was hampered by a lack of qualified instructors, standardized curricular, and accessible laboratories. Black recognized this deficiency, and he addressed it. He viewed the university as a vital setting for promoting scientific comprehension and nurturing future researchers. Black initiated his teaching career at the University of Glasgow, where he delivered lectures on chemistry and medicine. Subsequently, he relocated to the University of Edinburgh, which evolved into a focal point for scientific advancement. His lectures were celebrated for their lucidity, accuracy, and captivating demonstrations. Black highlighted the process of scientific exploration. He led his students through experiments, prompting them to observe meticulously, to challenge assumptions, and to formulate their own conclusions grounded in empirical evidence. This method distinguished him from many of his peers, who frequently depended on theoretical frameworks without adequate practical involvement. His lectures were carefully constructed presentations intended to both fascinate and educate. He incorporated a range of experimental demonstrations to clarify the principles he was explaining. These demonstrations were precisely prepared and performed, designed to elucidate intricate concepts in a clear and understandable way. He utilized these experiments to illustrate the theoretical principles he taught, and also to demonstrate the significance of careful observation and measurement. Black's lectures exemplified the effectiveness of experiential learning. He held the conviction that direct interaction with scientific phenomena was crucial for cultivating a genuine understanding of the natural world. He cultivated a culture of collaboration and intellectual exchange among his students. He fostered active participation in experiments, inviting challenges to his ideas and supporting the development of individual research projects. This collaborative setting was essential for cultivating scientific thought. He urged students to think critically, to examine assumptions, and to undertake their own research endeavors. He established an environment where students felt enabled to explore their concepts and pursue their scientific passions. Black's influence reached far beyond the classroom. He guided numerous students who subsequently made significant scientific contributions. These individuals, formed by Black's rigorous instruction and dedication to the experimental method, continued his work. They shared his ideas, expanded his research, and built their own scientific careers, upholding the principles he valued. His students often achieved distinction, strengthening his impact on science. Clear communication was another key aspect of Black's teaching. He recognized that scientific knowledge progressed through effective sharing. He could transform complex ideas into language understandable to many. He stressed the importance of precise language and clear presentation. His lectures exemplified lucid explanation, demonstrating how to present scientific findings in an informative and engaging way. Black's educational contributions remain pertinent today. His focus on experimental demonstrations, his dedication to clear communication, and his encouragement of student participation are practices that remain valuable in scientific education. His legacy highlights the importance of fostering a culture of inquiry, collaboration, and critical thinking in the pursuit of scientific knowledge. The principles he supported, including the importance of observation, the value of experimentation, and the necessity of clear communication, continue to shape how science is taught and practiced. His influence is evident in the modern emphasis on hands-on learning, the use of visual aids, and the promotion of collaborative research. Joseph Black's legacy as an educator demonstrates the transformative power of teaching. He imparted knowledge and inspired a generation of scientists to embrace the experimental method, value precision, and pursue their own intellectual curiosity. Black's influence as a teacher, a mentor, and a champion of scientific rigor ensured that his ideas would continue to shape the scientific landscape long after his research career. His commitment to education, combined with his scientific breakthroughs, established him as a pivotal figure in the history of science. His impact extended far beyond his laboratory, influencing the development of scientific thought and shaping the careers of countless individuals. The progress of science, built with observation, experimentation, and insightful deduction, often features figures whose contributions are both profound and multifaceted. Joseph Black a name associated with the beginning of modern chemistry and thermodynamics, serves as a prime example. His work, carefully created within the intellectual context of the 18th century, continues to be relevant, providing important lessons about scientific inquiry and its lasting impact on our understanding of the world. Black's legacy goes beyond a list of his discoveries. The concept of fixed air, the concept of latent heat, and the careful measurement of specific heat capacities are hallmarks of his genius, and the interconnectedness of these achievements truly defines his significance. He constructed a coherent framework, a new way to view the physical world. His approach featured a persistent drive for accuracy, a commitment to thorough experimentation, and an unyielding belief in the value of quantitative analysis. These aspects, working together, allowed him to uncover fundamental principles that previous generations of scientists had failed to grasp. The discovery of fixed air, later identified as carbon dioxide, was a turning point. It fundamentally altered the existing understanding of air as a simple, indivisible element. Black's experiments, involving the heating of magnesium carbonate and the subsequent release of this fixed air, showed that air was a complex substance capable of chemical changes. This recognition of air's composite nature initiated a new era of chemical investigation, leading to the discovery of other gases and a more advanced understanding of chemical reactions. The concept of latent heat, equally groundbreaking, revolutionized the study of heat. Before Black's work, heat was often seen as a simple manifestation of temperature. His careful observations of ice, water, and steam revealed that heat could be absorbed or released without a corresponding change in temperature. This phenomenon, which he called latent heat, showed that heat played a more complex role than previously thought, influencing the state of matter and driving phase transitions. This insight proved essential to the development of the steam engine, an invention that would reshape the industrial landscape and change the course of human history. Black's detailed exploration of specific heat capacities further enhanced this foundation. He introduced the concept of measuring the quantity of heat needed to raise the temperature of a substance by a specific degree. This quantification of heat, along with his understanding of latent heat, transformed the study of heat from a qualitative, descriptive field to a quantitative, measurable science. This quantitative approach, a key feature of Black's work, provided a new level of accuracy and predictive power, enabling scientists to make accurate calculations and create models of thermal behavior. Black's contributions encompassed more than laboratory work. He was a devoted educator, a mentor who inspired a generation of scientists. His lectures at the University of Edinburgh were celebrated for their clarity, rigor, and focus on experimental demonstration. He valued hands-on learning, encouraging his students to repeat his experiments and cultivate their own critical thinking skills. This dedication to education, combined with his scientific breakthroughs, secured his position as a key figure in the progress of scientific thought. The influence of Black's work is apparent in the development of chemistry and physics. His discoveries provided the essential basis for the development of thermodynamics, a branch of physics that concerns heat and its relationship to other forms of energy. His understanding of specific heat capacities is fundamental to the study of heat transfer and thermal properties of materials. Moreover, his meticulous approach to experimentation and his emphasis on quantitative analysis established a standard for scientific rigor that remains relevant today. His influence is also visible in the ongoing pursuit of scientific education. Black's commitment to clarity, precision, and the importance of experimental demonstration continues to shape how science is taught and practiced. His legacy encourages us to approach the world with curiosity, to value empirical evidence, and to seek a deeper understanding of the fundamental principles that govern the universe. Black's work demonstrates the power of careful observation, rigorous experimentation, and insightful analysis. He discovered new phenomena and fundamentally reshaped our understanding of heat, matter, and the nature of scientific inquiry. His legacy extends beyond textbooks or laboratory protocols. It influences our thought processes, our methods for solving problems, and our admiration for the intricate beauty of the physical world. Joseph Black, a significant figure in scientific advancement, made a lasting impact. His work continues to clarify the path to a more thorough understanding of the universe, highlighting the lasting importance of curiosity, accuracy, and the constant search for knowledge. His legacy serves as a guide, leading us to a deeper comprehension of the world and our position within it.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.